March 8th, 1952, 6:42 a.m. Consolidation Coal Mine Number 9, Farmington, West Virginia. Temperature at the mine face, 58 degrees Fahrenheit. Humidity, 87%. The shift has been running for 42 minutes when Jimmy Watkins, 19 years old and 7 months into his job as mine electrician, kneels beside the main ventilation control panel checking voltage readings that have been fluctuating for the past week. The panel is a gray metal box bolted to the tunnel wall 2,800 feet from the surface, covered in switches and gauges and wiring that Jimmy has memorized over months of daily maintenance. His headlamp beam plays across the dials as he records readings in a small notebook. Voltage steady at 240, amperage at 32, fan motor running at 1,750 RPM. Behind him, the main tunnel stretches 600 feet to where 127 miners work the coal face with picks and pneumatic drills, the sound of metal on rock creating a constant percussion that echoes through the confined space. The explosion comes without warning at 6:43 a.m. Jimmy will later describe it as feeling like the mountain punched him in the chest, a pressure wave that travels faster than sound, faster than thought, a wall of force that lifts him off his feet and slams him against the tunnel wall with enough impact to crack 2 ribs. The sound follows a fraction of a second later, a deep, booming roar that seems to come from everywhere at once, from the rock itself, a noise so loud it bypasses his ears entirely and vibrates directly through his bones. His headlamp goes out. The tunnel's electric lights go out. For 3 seconds, there is absolute darkness and a silence so complete it feels like the world has ended. Then the screaming starts. Jimmy's training takes over before conscious thought returns. He fumbles for the spare battery in his tool belt, a 6-volt unit he carries for exactly this kind of emergency, and connects it to his headlamp with fingers that shake but still remember the motions from hundreds of repetitions. Light returns, showing him a tunnel transformed into chaos. The ventilation panel hangs open, its door blown off the hinges, wiring visible inside smoking and sparking. The main power cable that runs along the ceiling has separated from its mounting brackets and dangles in loose coils. Dust fills the air so thick he can taste it, coal dust and rock dust and something else, something that makes his eyes water and his throat burn. Methane, the smell of rotten eggs that every miner learns to recognize because it means death is in the air. He forces himself to his feet despite the pain in his ribs and immediately understands the situation with the clarity that comes from 7 months of daily exposure to mine safety protocols. The explosion originated deeper in the mine, probably near the coal face where methane pockets sometimes accumulate despite the ventilation. The blast collapsed something, probably the main shaft based on the direction of the pressure wave, which means they're trapped. The power failure killed the ventilation fans, which means fresh air has stopped flowing into the mine. The 127 miners deeper in the tunnel are depending on air circulation to stay alive, and without it, they have maybe 3 hours before carbon dioxide and methane concentrations reach lethal levels. Less if anyone panics and starts breathing hard. Jimmy reaches the first group of miners at 6:47 a.m., 4 minutes after the explosion. They're huddled in a side tunnel, covered in dust, some bleeding from cuts caused by flying rock fragments. Thomas Riley, the shift foreman and a man with 23 years underground experience, grabs Jimmy's shoulder. What happened? His voice is steady despite the blood running from a gash on his forehead. Methane explosion, Jimmy says. Main shaft is probably collapsed. Power's out. Ventilation's down. He doesn't need to explain what that means. Every man in the tunnel knows that without air circulation, they're in a race against suffocation. How long? Riley asks. Jimmy does the math in his head, calculations learned in the technical college classes he took 3 nights a week for the past year. The tunnel system contains approximately 420,000 cubic feet of airspace. With 128 men breathing at an average rate of 15 breaths per minute, consuming roughly 0.5 cubic feet per breath, they'll deplete the oxygen from 21% to 17% in about 2 hours. At 17%, men start getting confused, clumsy. At 15%, they pass out. At 12%, brain damage. 2 hours until we start having problems, he says. 3 hours maximum. Then we're unconscious. He doesn't mention the 4-hour mark because he doesn't need to. Dead is dead. The The next 30 minutes are a blur of organized chaos. Riley orders all miners to gather in the main tunnel 200 feet from the control panel, the widest section with the most airspace. He sends 2 men to check the escape shaft, though everyone knows it's probably blocked if the main shaft collapsed. He establishes a head count. 127 miners plus Jimmy equals 128 total. No one is missing, which means everyone who came down this morning is still alive. That might change soon. Jimmy returns to the ventilation control panel, his headlamp illuminating the damaged equipment, and assesses what he's working with. The main power cable is dead, severed somewhere between the panel and the surface. The backup generator, located 400 feet up the tunnel, failed to activate, probably because its fuel line ruptured in the explosion. The ventilation fans themselves are undamaged, their motors visible 30 feet up the tunnel where they're mounted in a side shaft. But motors need electricity, and electricity needs a circuit, and the circuit is broken in at least 3 places that Jimmy can see, and probably a dozen places he can't. The panel's wiring is a disaster. Insulation melted, connections loose. The main relay switch cracked. By every standard Jimmy learned in technical college, this system is unfixable without replacement parts and proper tools and several hours of careful work. But Jimmy isn't thinking about proper repair procedures. He's thinking about a car battery. The mine keeps emergency equipment stored in a wooden box 50 feet from the control panel. First aid supplies, spare lamp batteries, hand tools, and one 12-volt car battery connected to a portable radio for communication during emergencies. The battery is meant to power the radio for maybe 6 hours. Jimmy is wondering if it could power the ventilation fans long enough to matter. The fans need 240 volts to run properly, and the battery only provides 12, which means they won't run at full speed, won't move nearly as much air as normal. But some air is infinitely better than no air. At 7:18 a.m., 36 minutes after the explosion, Jimmy retrieves the car battery from the emergency box. It weighs 42 pounds, its black plastic case scuffed from years of service, terminals crusted with white corrosion. He carries it to the control panel and sets it down, then starts gathering wire. The mine has copper wire everywhere, in the control panel, in the damaged power cables, in the lamp circuits that run along the tunnel walls. He needs approximately 40 feet to create a circuit from the battery to the fan motors, and he needs it thick enough to handle the current without overheating. Thin wire will melt. Too thick won't be flexible enough to work with in the confined space. He strips wire from the damaged power cable using a pocket knife, cutting away melted insulation, salvaging sections that are still functional. His hands work steadily despite his broken ribs, sending sharp pains through his chest with every movement. Riley appears beside him with 2 other miners, Carl Henderson and Mike O'Brien, both experienced electricians who worked in the mine's surface shop before transferring underground. "Tell us what you need," Riley says. Jimmy explains his plan in short sentences. Bypass the control panel completely. Run direct wire from the battery to the fan motors. Create a simple circuit without relays or safeties. Henderson shakes his head. The fans need 240 volts. That battery's only 12. It won't work. "It'll work," Jimmy says, his voice more confident than he feels. "The motors will run on 12 volts. Not at full speed, but they'll turn. Slow fan is better than no fan." He doesn't mention that he's never actually tried this, that everything he knows about motors and voltage comes from textbooks and theory rather than practice. He doesn't mention that the fans might burn out their motors trying to run on insufficient voltage. He doesn't mention that even if everything works perfectly, the battery will probably die in 6 or 7 hours, well before rescue teams can dig through whatever collapsed above them. He says only what matters. It'll buy us time. They work in near-complete silence, the only sounds their breathing and the scrape of wire against rock as they run the circuit up the tunnel wall. Jimmy splices connections using techniques learned in technical college, twisting bare copper together and wrapping the joints with electrical tape from his tool belt. Henderson and O'Brien hold the wire in place while he works, their headlamps providing illumination. Every movement must be precise because they get one chance at this. The battery has a finite amount of stored electricity, and every mistake, every short circuit, every inefficient connection wastes power they can't replace. At 8:03 a.m., 1 hour and 21 minutes after the explosion, the circuit is complete. 40 feet of salvaged copper wire runs from the battery terminals at the control panel, up the tunnel wall, across the ceiling on makeshift brackets made from bent nails, and down to the fan motor terminals in their housing 30 feet away. Jimmy checks every connection twice, looking for loose wire, exposed metal that might touch the tunnel wall and create a short, any flaw that could prevent current flow. His hands leave black smudges on the wire, a mixture of coal dust and blood from cuts he doesn't remember getting. The miners have fallen silent, 127 men watching a 19-year-old kid prepare to connect a car battery to machinery that normally runs on 20 times the voltage, betting all their lives that physics and desperation can combine into salvation. "Everyone move back," Jimmy says. "If the circuit shorts, if something sparks in an atmosphere increasingly heavy with methane, the resulting explosion will kill anyone standing close." The miners retreat 50 feet up the tunnel, leaving Jimmy alone with the battery and the switch he's created from 2 pieces of bare wire. He holds the wires 1 inch apart, positive in his right hand, negative in his left, and takes a breath that tastes of dust and fear. Then he touches the wires together. For 1 terrible second, nothing happens. No spark, no sound, no indication that electricity is flowing. Jimmy feels his heart hammering against his broken ribs, feels the weight of 127 lives pressing down on him with almost physical force. Then he hears it, a low hum from the motor housing, a vibration that travels through the floor beneath his knees. The hum becomes a whir. The whir becomes a steady rotating sound as the fan blades begin to turn, slowly, far slower than their designed speed, but turning nonetheless. Air begins to move. Jimmy can feel it on his face, a gentle current flowing from deep in the tunnel toward the blocked main shaft, carrying away carbon dioxide and methane, replacing it with whatever oxygen remains in the tunnel system. The sound that goes up from 127 miners is something between a cheer and a sob. Jimmy doesn't hear it. He's focused entirely on the circuit, watching for any sign of overheating, listening for changes in the motor sound that might indicate impending failure. The wire he spliced together is warm, but not hot. The battery terminals show no unusual sparking. The fan blades continue their steady rotation, audible now as a rhythmic whisper in the confined space. According to his mental calculations, the battery should power the fans for approximately 6 to 7 hours before its charge depletes to the point where the motors stop. Rescue teams will need longer than that to dig through the collapsed shaft. But 6 hours of fresh air circulation means 6 more hours of consciousness, 6 more hours to find another solution, 6 more hours of life. At 8:15 a.m., Jimmy allows himself to sit down, leaning against the tunnel wall, feeling the pain in his ribs settle into a steady throb. Henderson sits beside him, and for a moment, neither speaks. Then Henderson says, "Where'd you learn to do that?" Jimmy shrugs, the motion sending fresh pain through his chest. "Technical college, Tuesday and Thursday nights, electrical theory." He doesn't mention that the textbook never covered using car batteries to power industrial ventilation fans. He doesn't mention that he made up most of the wiring technique as he went along, combining theory with desperation. He says only, "Needed the credits to move up to surface electrician. Pays better." The next 6 hours will test whether Jimmy's improvised circuit can sustain 128 men long enough for rescue to arrive. The battery's voltage will drop slowly but steadily, from 12 volts at the start to 10.8 volts by 10 a.m. to 9.2 volts by noon. The fan speed will decrease correspondingly, the airflow diminishing from an estimated 400 cubic feet per minute to 250 by mid-morning. Jimmy will monitor the system constantly, checking connections, measuring voltage with a simple multimeter from the emergency kit, calculating and recalculating how much time they have left. At 11:30 a.m., he'll add a second battery salvaged from a mining cart's electrical system, connecting it in series to boost voltage back up temporarily. The extra power will buy them 2 more hours, but that knowledge lives in the future. Right now, at 8:15 a.m. on March 8, 1952, sitting in a coal mine 2,800 feet underground with 127 other men and air moving through a circuit that shouldn't work but does, Jimmy Watkins experiences something that will stay with him for the rest of his life: the absolute clarity of having made a decision that mattered more than any decision he will ever make again. The battery hums, the fans turn, the air moves, and 128 men breathe and keep breathing, waiting for rescue they hope is coming, sustained by 12 volts and 40 feet of wire, and one teenager's refusal to accept that improvisation isn't the same as impossibility. Thomas Riley, the shift foreman with 23 years of experience and the authority to make command decisions in emergencies, sits down on Jimmy's other side. He pulls out a cigarette, then thinks better of it given the methane levels, and puts it away. "You realize," Riley says quietly, "that you just did something that's not in any mining manual ever written." Jimmy nods, too tired to speak. "You realize," Riley continues, "that if this had gone wrong, if the battery had sparked wrong and ignited the methane, you'd have killed everyone here." Jimmy nods again. He knows. He'd known when he touched those wires together. "But you did it anyway," Riley says, and there's something in his voice that Jimmy will remember decades later when he's training new electricians and teaching them that sometimes the textbook solution isn't available, and you have to trust physics and courage and the simple fact that doing something is always better than doing nothing. "Yeah," Jimmy says, "did it anyway." Because 127 men were depending on air, and air needed electricity, and electricity needed a circuit, and the only person who could create that circuit was a 19-year-old kid with 7 months of mine experience and 2 years of night school education, who understood that the difference between life and death can come down to whether you're willing to strip 40 feet of wire and trust that basic electrical theory translates into practice, even when you're improvising in the dark. The miners settle in for what everyone understands will be a long wait. Someone starts a head count every 30 minutes to ensure no one wanders off into side tunnels and gets lost. Someone else organizes the remaining food, mainly lunch pails brought down for the shift, redistributing it evenly. Water is rationed from the 4 barrels kept at the workface. Carl Henderson, drawing on his surface shop experience, improvises a voltage divider using resistors from broken equipment, creating a monitoring system that lets them track battery drain more precisely. Mike O'Brien starts marking time on the tunnel wall with chalk, a simple tally system that will eventually show 14 marks, one for each hour they spend underground. Jimmy returns to the control panel at 9 a.m. to check the circuit. The wire joints are holding. The battery terminals show normal discharge patterns. The fans continue their steady rotation, slower than optimal but sufficient to maintain livable air quality. He pulls out his notebook and records measurements. Battery voltage 10.4 volts. Fan speed estimated at 300 RPM. Air temperature 62 degrees. Time elapsed 2 hours, 18 minutes. The numbers are precise, factual, stripped of emotion. They don't reflect the knot of fear in his stomach, or the constant pain in his ribs, or the knowledge that when the battery dies, they'll have maybe 90 minutes before carbon dioxide levels become critical. They're just numbers, the kind engineers use to evaluate system performance. At 10:45 a.m., 4 hours after the explosion, the first sounds of rescue reach them. A distant rhythmic pounding, metal on rock, echoing down through the collapsed main shaft. The miners stop talking, listening to that steady beat that means someone above knows they're alive and is digging toward them. Riley calculates distances and rates. The collapse probably blocked 200 feet of shaft. Rescue crews using pneumatic drills can clear maybe 15 feet per hour, which means 13-14 hours until breakthrough. Jimmy looks at his battery voltage reading 9.8 volts and dropping. The math is brutal. The battery won't last 13 hours. Even with the second battery he added at 11:30, they'll run out of power around 4 p.m. After that, they'll have their own breath and whatever air remains in the tunnel system. But knowledge of future failure doesn't change present action. Jimmy continues monitoring the circuit, making small adjustments to maximize efficiency. He tightens loose connections that have vibrated loose from the fan motor's operation. He redistributes weight on the wire supports to prevent sagging that might cause shorts. He checks the battery terminals every 30 minutes, cleaning corrosion that builds up and impedes current flow. Each action is small, technical, focused on the immediate problem of keeping electricity flowing through a circuit that exists only because he refused to accept that proper procedure was more important than survival. At noon, 6 hours after the explosion, the battery voltage has dropped to 9.2. Fan speed has decreased to an estimated 200 RPM. Air circulation is noticeably slower, and some miners are complaining of headaches, an early symptom of elevated carbon dioxide levels. Jimmy does another calculation. At current air circulation rates, they can maintain consciousness for approximately 4 more hours, which puts them at 4 p.m. Rescue is still digging, but their progress has slowed as they encounter harder rock layers. The sound of drilling is clearer now, close enough that they can distinguish individual impacts, but still distant enough that breakthrough isn't imminent. Carl Henderson approaches Jimmy at the control panel. "We need more power," he says simply. Jimmy nods. He's been thinking about this problem for the past hour. The mining cart battery he added earlier boosted voltage temporarily, but it's draining faster than the original car battery because it's older and hasn't been properly maintained. What they need is more stored electricity, but there are no more batteries in the mine. Henderson seems to read his thoughts. "What about the lamp batteries?" he suggests. "Everyone brought one down. That's 128 batteries, 6 volts each." Jimmy considers this. Individual lamp batteries are small, designed to power a single headlamp for 8 to 10 hours. Each one stores maybe 1.5 amp hours of charge, compared to the car battery's 50 amp hours. But 128 small batteries connected in the right configuration could provide significant power. The problem is connecting them. Each battery has screw terminals, and connecting 128 batteries in series would create 768 volts, far too much. But connecting them in parallel would keep voltage at 6 and multiply the amp hours by 128, giving them approximately 190 amp hours total, more than 3 times what the car battery provided. "We'd need wire," Jimmy says. "Lots of wire. And it would take time to connect them all." Henderson nods toward the tunnel where 127 miners sit waiting. "We got time. We got wire. And everyone here knows how to strip insulation and twist connections. Put us to work." Jimmy thinks for exactly 5 seconds, running the math. Time to collect batteries, time to strip wire, time to connect 128 parallel circuits, time to integrate the new power source into the existing fan circuit. 2 hours minimum. But if it works, they'll have enough power to run the fans until rescue breaks through, or at least come close enough that the difference won't matter. At 12:15 p.m., Jimmy explains the plan to Riley. The foreman listens, asks 3 technical questions about voltage compatibility and connection methods, then nods. "Do it," he says. Within 10 minutes, every miner has surrendered his lamp battery. They work in darkness now except for Jimmy's lamp, and 2 others kept operational for safety. Carl Henderson organizes teams. One group strips wire from abandoned lamp circuits. Another group cleans battery terminals. A third begins connecting batteries in pairs. Jimmy supervises the parallel circuit construction, checking each connection to ensure proper polarity, because one reversed battery would create a short and potentially destroy the entire system. The work takes exactly 1 hour and 47 minutes. At 2:02 p.m., 7 hours and 20 minutes after the explosion, Jimmy connects the last wire in the lamp battery array. 128 6-volt batteries, connected in parallel, creating a power source with approximately 190 amp hours of capacity at 6 volts. He splices this array into the existing fan circuit, replacing the failing car batteries. The voltage drops from 8.4 to 6.0, and the fan speed decreases noticeably. But the amp-hour capacity has quadrupled. By Jimmy's calculations, this new power source should sustain the fans for another 8 to 10 hours, which puts them past 10 p.m., well beyond when rescue should break through. The fans continue turning, their sound unchanged except for a slightly lower pitch corresponding to the reduced voltage. Air continues circulating, carrying away carbon dioxide and methane, maintaining oxygen levels at marginally safe concentrations. The miners return to waiting, now in almost complete darkness, conserving the few remaining lamp batteries for essential use. The drilling sounds grow louder overhead, and someone estimates rescue is within 50 feet now, maybe 2 hours away. Jimmy sits beside his improvised circuit, monitoring by touch what he can no longer see clearly, feeling the warmth of current flowing through wire, the vibration of fan motors turning, the physical manifestation of electrical theory translated into practice. At 4:30 p.m., 9 hours and 48 minutes after the explosion, light appears in the main shaft. Not daylight, but the harsh white beam of rescue team floodlights shining down through a hole 3 feet in diameter where the collapsed section used to be. Cheers echo through the tunnel, loud enough to momentarily drown out the fans. The hole widens over the next 40 minutes as crews clear remaining debris. At 5:12 p.m., the first rescuer descends on a rope, a mine safety inspector named Robert Walsh, who does a rapid head count and air quality check before radioing to the surface. All 128 alive. Air quality marginal but survivable. Begin evacuation. The evacuation takes 2 hours. Injured men go first, including 3 with broken bones and 1 with a suspected concussion. Then the older miners, the ones most affected by carbon dioxide exposure. Jimmy goes up in the final group at 7:23 p.m., exactly 12 hours and 41 minutes after the explosion that started everything. He leaves his circuit behind, still running, still pushing air through the tunnel, powered by 128 lamp batteries connected by 200 feet of stripped wire and held together by improvisation and desperate need. The circuit will run for another 3 hours before the batteries finally die, but by then, everyone is safe on the surface, and it doesn't matter anymore. The photograph will be taken 4 days later, on March 12, 1952, by a photographer from the Charleston Gazette. It shows a young man in mine coveralls and a safety helmet kneeling beside a control panel in a tunnel, one hand on a car battery, the other on a tangle of wire. The lighting is artificial, set up specifically for the photo, and the scene has been partially reconstructed for documentation purposes. The real circuit has been dismantled, analyzed by safety inspectors, and preserved as evidence in the incident report. But the photograph captures something essential, a moment when ordinary tools became instruments of survival, when textbook theory met desperate practice, and when a 19-year-old electrician with 7 months of experience made a decision that kept 127 men breathing long enough to see daylight again. If you look closely at Jimmy's face in that photograph, you can see exhaustion written in the circles under his eyes and the slump of his shoulders. You can see the careful attention he's paying to the equipment, even though this is a reconstruction and nothing here is actually dangerous. But what you can't see in the photograph, what no image can capture, is the weight of those 14 hours underground, the constant monitoring of voltage levels, the calculations done over and over in his head, remaining battery life versus estimated rescue time, the knowledge that every minute his circuit kept running was another minute of life for 128 men, the fear that the battery would die before rescue arrived, and the determination to squeeze every possible amp hour from every available power source, even if it meant working in darkness with broken ribs. Jimmy Watkins will work in coal mines for another 23 years, eventually becoming chief electrical engineer for the entire Consolidation coal operation in West Virginia. He'll train 47 electricians over those years, and every one of them will hear the story of March 8, 1952, usually told in the same matter-of-fact tone Jimmy uses for all technical instruction: problem identification, available resources, improvised solution, measured results. He won't mention the fear or the pain or the responsibility. He'll focus on the circuit, the voltage calculations, the parallel connection technique that allowed multiple small batteries to function as one large power source. The story will become legend in mining circles, taught in safety courses as an example of emergency improvisation. But the official recognition will come much sooner. On April 15, 1952, the West Virginia Mining Commission will award Jimmy the Medal of Industrial Heroism, the state's highest civilian honor for mine safety. The citation will read, "For exceptional courage and technical skill in creating an emergency ventilation system that sustained 128 men for 14 hours following the Consolidation No. 9 mine collapse. His improvised electrical circuit, created from salvaged materials under extreme conditions, represents the highest standards of practical engineering and personal bravery." The medal ceremony will be held at the state capitol in Charleston, with Governor O.K. Pattison presenting the award. Jimmy will shake the governor's hand, pose for photographs, give a brief speech written mostly by other people, and then return to Farmington and back underground, because mining is what he knows, and fixing electrical systems is what he does. The technical analysis of Jimmy's circuit, conducted by engineering professors from West Virginia University, will be published in the Journal of Mine Safety in August 1952. The paper, titled Emergency Ventilation Techniques, a Case Study in Improvised Electrical Systems, runs 12 pages and includes detailed schematics of the battery connections and fan motor modifications. The conclusion notes that while the circuit violated multiple electrical codes and safety regulations, it represented sound application of basic electrical principles under emergency conditions. The paper will become required reading in mining engineering programs across the United States. But for the 127 miners who spent 14 hours underground breathing air circulated by a car battery and 40 feet of wire, the technical analysis in metals and academic papers miss something essential. They remember the sound of the fans starting up when Jimmy touched those wires together. They remember the feel of air moving across their faces in the darkness. They remember watching a 19-year-old kid with broken ribs spend hour after hour monitoring connections and checking voltage and refusing to accept that improvised meant inadequate. They remember that when civilization systems failed 2,800 feet underground, when the power grid and the backup generators and all the engineered safety systems became useless, it was basic knowledge and simple tools and one person's refusal to give up that kept them alive. Thomas Riley, the shift foreman who made the decision to let Jimmy try his improvised circuit, will retire from mining in 1967 after 38 years underground. At his retirement party, attended by 200 current and former miners, he'll tell the story of March 8, 1952 one more time. He'll describe the moment when Jimmy touched those wires together and nothing happened, that terrible second when it seemed like desperation wasn't going to be enough. Then he'll describe the sound of the fan motor starting, a sound that meant life instead of death. And he'll end by saying something that everyone in that room already knows. Heroism isn't about not being scared. It's about being scared and doing what needs doing anyway. Jimmy was terrified. We all were. But he had knowledge and tools and 127 reasons to make it work. So he made it work. Jimmy Watkins will die in 1998 at age 65. Not from mining injuries, but from lung cancer that probably started in those 23 years breathing coal dust. His obituary in the Charleston Gazette will mention his career, his family, his community involvement. It will mention the Medal of Industrial Heroism and the 1952 rescue. But it won't capture what he gave to 127 men on a March morning when the mountain collapsed and the power failed, and survival came down to whether a teenager's improvised circuit could cheat death for 14 hours. That knowledge lives only in memory, in the minds of the men who were there, the men who breathed air pushed by fans powered by batteries connected by salvaged wire, held together by electrical tape and desperation. The car battery from that March morning, serial number E42876, will be preserved by the West Virginia Mining Museum in Beckley. It sits in a climate-controlled case, its terminals still showing traces of the corrosion Jimmy cleaned away every 30 minutes to maintain current flow. A placard beside it explains its history in language carefully crafted to be accessible to museum visitors who don't know electrical theory. This 12-volt automotive battery, combined with improvised wiring, powered emergency ventilation fans that sustained 128 trapped miners for 14 hours in 1952. The circuit should not have worked according to standard engineering principles, but electrical technician Jimmy Watkins bypassed the damaged control systems and created a direct connection that proved adequate to maintain life-sustaining air circulation until rescue teams completed their work. But that placard, like all museum placards, reduces complexity to simplicity for the sake of public understanding. It says the circuit should not have worked, when what it means is that the circuit should not have been necessary because proper safety systems should have prevented the collapse or provided redundant emergency power. It says Watkins created a direct connection, when what it means is that he stripped wire from damaged cables with a pocket knife while his broken ribs ground against each other and his hands shook from fear and adrenaline. It says the circuit proved adequate, when what it means is that 128 men emerged from that mine alive, because a 19-year-old electrician understood that physics doesn't care about regulations, that electricity flows through any complete circuit regardless of whether that circuit meets code, and that sometimes the only thing standing between life and death is whether you're willing to trust theory enough to bet lives on it. The mine itself, Consolidation Number 9, will be permanently closed in 1968, after another methane explosion kills 78 miners despite all the improved safety systems installed after 1952. That disaster will lead to the Federal Coal Mine Health and Safety Act of 1969, which establishes the first comprehensive national standards for mine safety. The Act's electrical system requirements will be based partly on lessons learned from Jimmy's improvised circuit. the need for redundant power sources, the importance of basic electrical knowledge for all mine electricians, the requirement for emergency batteries capable of sustaining ventilation for minimum 24 hours. Jimmy will serve as a consultant during the act's development, providing technical expertise based on his 16 years of experience by that point. But in March 1952, none of that future exists. There's only the present: a collapsed mine, failing power systems, 128 men depending on air circulation, and one teenager with a car battery and 40 feet of wire, proving that sometimes the difference between tragedy and survival is as simple and as complex as understanding that electricity plus motor equals fan, and fan equals air, and air equals life. The rest is just engineering. The rescue begins at 5:12 p.m. on March 8, 1952, when Mine Safety Inspector Robert Walsh descends through the newly cleared opening in the main shaft, his boots finding purchase on the rope ladder that rescue crews have lowered from the surface. The hole is barely 3 feet in diameter, cut through 180 feet of collapsed rock and timber using pneumatic drills that have been running continuously for 10 hours and 30 minutes. Walsh carries a portable gas detector in his left hand, its needle already swinging toward dangerous levels as he enters the mine atmosphere. Carbon dioxide, 4.2%, well above the 2.5% safety threshold. Oxygen, 17.8%, below the normal 21%, but sufficient to sustain life. Methane, 0.8%, approaching the 1.0% level, where any spark could trigger another explosion. The numbers tell a simple story. 128 men have been breathing in a confined space for more than 10 hours, and the air is on the edge of becoming unbreathable. Walsh's headlamp illuminates the tunnel as he drops the final 12 feet to the floor, landing in a crouch that sends up a small cloud of coal dust. The scene that greets him is something he'll describe in his official report with careful technical language, but in private conversations for the rest of his life, he'll use different words: miraculous, impossible, a testament to what humans can endure when failure means death. 127 miners sit or lie along the tunnel walls, most conscious but showing signs of carbon dioxide poisoning, headaches, confusion, slurred speech. 3 men have obvious injuries: broken bones, lacerations, one possible concussion. But everyone is alive. Everyone is responsive. And the reason becomes clear when Walsh hears the sound: a low mechanical whir echoing from deeper in the tunnel, the unmistakable rhythm of ventilation fans still running despite the complete power failure. He follows the sound to the control panel 200 feet into the tunnel, where he finds Jimmy Watkins sitting cross-legged on the floor, one hand resting on what appears to be a car battery connected to a massive tangle of wires that run up the tunnel wall and disappear into the darkness. The young electrician looks up as Walsh approaches, his face so covered in coal dust that only his eyes show white, and says in a voice hoarse from 10 hours of breathing bad air, "Fans are still running. Battery's got maybe 2 more hours in it. We would have made it even if you'd taken longer." There's no pride in the statement, no drama, just the factual assessment of a technician reporting on system performance. Walsh will later tell investigators that his first thought upon seeing Jimmy's improvised circuit was that it violated approximately 17 different mine safety regulations. His second thought was that those regulations were written for normal operations, not survival situations. His third thought, the one that will stay with him, is that whoever trained this kid deserves a medal because theory is useless if you can't translate it into practice when everything is falling apart. He keys his radio, the signal boosted by a repeater the rescue team set up at the shaft entrance, and transmits the message that will reach the surface 2,800 feet above. All 128 alive, air quality marginal but survivable. Begin evacuation. The evacuation procedure, designed during the long hours while rescue crews drilled through collapsed rock, prioritizes the most vulnerable first. 3 miners with serious injuries go up immediately, strapped into wire baskets that are hauled to the surface by diesel winches. The process takes 12 minutes per person. Secure the basket, signal the surface crew, maintain steady communication during the 180-foot ascent, ensure the person reaches safety before lowering the basket for the next evacuation. At that rate, evacuating all 128 men will require 25 hours and 36 minutes, but Walsh implements a faster protocol once he confirms the shaft is stable. 2 men per basket for those who are uninjured, cutting the time to approximately 13 hours. Thomas Riley, the shift foreman, organizes the evacuation with the same methodical competence he's applied to every task over his 23-year mining career. Injured first, then oldest, then youngest. He writes names in chalk on the tunnel wall, maintaining a roster to ensure nobody gets forgotten in the confusion. Carl Henderson goes up in the 4th basket at 5:47 p.m. Mike O'Brien follows at 6:01 p.m. By 7 p.m., 43 men have reached the surface, and the process has settled into a steady rhythm. Basket down, 2 men in, basket up, repeat. The tunnel gradually empties as miners ascend to daylight they haven't seen in more than 12 hours. Jimmy remains at his circuit, monitoring the battery voltage even though evacuation has begun. The lamp battery array is down to 4.2 volts, well below its nominal 6-volt rating, and the fan speed has decreased noticeably. But the motors continue turning, continue pushing air, continue doing the job Jimmy designed them to do. Walsh crouches beside him at 6:30 p.m. and examines the circuit with the professional interest of someone who understands electrical systems. "This shouldn't work," he says finally. "Motor needs 240 volts. You're feeding it maybe 4. Basic electrical theory says the motor should have stalled out hours ago." Jimmy nods, too tired to explain the nuances. But he does anyway, because explaining technical problems is what electricians do. "Motor needs 240 volts for rated load," he says. "Rated load is moving maximum airflow against maximum resistance. We're not running maximum airflow. We're running maybe 15% of capacity, just enough to circulate air in a tunnel system that's mostly sealed. Low voltage means low torque, but we don't need high torque. We just need rotation." He gestures at the wire running up to the fan motors. "Every system has a minimum operational threshold. I calculated we'd hit that threshold around 3 volts. We're at 4.2, so we're still above minimum. Once we drop below 3, the motor will stall. But by my estimate, that won't happen for another 90 minutes. Walsh absorbs this, filing it away for the technical report he'll write later. Then he asks the question that matters more than theory. "How'd you know it would work?" Jimmy considers this for a long moment before answering. "Didn't know," he admits. "Calculated, estimated, hoped. But when the alternative is doing nothing and watching 127 men suffocate, you take calculated risks." He looks at Walsh with eyes that seem older than his 19 years. "Risk assessment isn't about avoiding danger. It's about choosing which danger is acceptable. Doing nothing was guaranteed death. Trying the battery was probable success. So I tried the battery." The evacuation continues through the evening. By 8:02 p.m., 78 men have reached the surface. The rescue operation has become routine enough that Walsh feels comfortable leaving the tunnel to coordinate with surface teams, leaving 2 junior inspectors to monitor the remaining evacuations. Jimmy finally agrees to disconnect his circuit at 8:15 p.m. after Walsh points out that with more than half the men evacuated, the remaining airspace contains sufficient oxygen even without fan circulation. He uses his pocket knife to cut the wires connecting the battery array to the fan motors, and the sound that has been a constant companion for the past 10 hours finally stops. The silence feels unnatural, oppressive, a reminder that the only thing that stood between 128 men and asphyxiation was electrical current flowing through salvaged wire. Jimmy ascends in the final group at 7:23 p.m. Wait, that's not right. Let me recalculate the timeline. The evacuation started at 5:12 p.m., and with 2 men per basket taking 6 minutes per cycle, we get approximately 20 men per hour. With 128 total, minus the first 3 injured who went individually, that's 125 men divided by 20 per hour equals 6.25 hours, putting the final evacuation around 11:27 p.m. Let me correct this timeline. Jimmy ascends in the final group at 11:23 p.m., exactly 16 hours and 41 minutes after the initial explosion. He climbs into the wire basket with Thomas Riley, the 2 of them fitting awkwardly in a space designed for 1 person lying down. The basket sways as the winch cable takes tension, and then they're rising through the darkness, the tunnel walls sliding past in the beam of Jimmy's headlamp. The ascent takes 7 minutes, 180 feet of vertical travel through the shaft that collapsed this morning, now shored up with timber supports installed by rescue crews. They pass through strata of different rock, coal seams, sandstone layers, shale formations, each visible as distinct bands in the excavated walls. The surface appears first as a lightening of the darkness, then as a distinct circle of brightness that grows as they ascend. The basket clears the shaft opening at 11:30 p.m., and Jimmy experiences a sensory overload that will take days to fully process. The temperature is 41 degrees Fahrenheit, 17 degrees colder than the tunnel. The air smells of diesel exhaust from the rescue equipment, of mud churned up by heavy machinery, of pine trees surrounding the mine entrance. Electric floodlights mounted on portable towers illuminate the area with harsh white light that makes Jimmy's eyes water after 16 hours in darkness broken only by headlamps. And there are people, dozens of rescue workers, mine officials, emergency medical personnel, and beyond the security perimeter, hundreds of family members and townspeople who have been gathering since the explosion was reported at 6:58 a.m. Medical personnel surround the basket before Jimmy can climb out. A nurse checks his pupils with a penlight, another takes his pulse and blood pressure. A doctor listens to his breathing with a stethoscope and asks questions about pain levels and consciousness during the ordeal. Jimmy answers mechanically, yes, he has chest pain from broken ribs. No, he never lost consciousness. Yes, he maintained cognitive function throughout. The medical team wants to transport him to Charleston Memorial Hospital for x-rays and observation. Jimmy refuses. I'm fine, he says. The word's automatic despite the fact that he's absolutely not fine. His ribs are screaming with every breath and his hands are shaking from 16 hours of adrenaline and exhaustion. I need to go home. But before he can leave, a mine official in a clean suit and tie intercepts him. The man introduces himself as Robert Harrison, Regional Director for Consolidation Coal Company, and he has questions. Lots of questions. The questions start technical. What voltage did you use? What wire gauge? What was the calculated current draw? What safety factors did you consider? Jimmy answers each question with precision, drawing diagrams on a clipboard someone provides, explaining series versus parallel connections, voltage drop calculations, motor torque requirements at low power. Harrison takes notes rapidly, occasionally asking follow-up questions that reveal his own engineering background. Then the questions shift to operational. Who authorized you to modify the ventilation system? Did you consult the shift foreman before proceeding? Were other electricians involved in the circuit construction? These questions carry different weight, the implications clear. Someone needs to determine whether Jimmy saved 127 lives or violated safety protocols that exist for good reasons. Jimmy's answers remain factual. Foreman Riley was informed and approved. Electricians Henderson and O'Brien assisted with wire installation. The decision was made collectively based on the immediate survival threat. He doesn't mention that approval consisted of Riley listening to the plan for 30 seconds and saying, "Do it," or that collective decision meant nobody had time to debate alternatives. Harrison's final question is the one that matters. Mr. Watkins, in your professional judgment, would these men have survived without your improvised ventilation system? Jimmy considers this carefully before answering. In my professional judgment, he says slowly, carbon dioxide levels would have reached 8% within 3 hours of the explosion. At that concentration, unconsciousness occurs within minutes. Without the fans maintaining air circulation, all 128 men would have been dead by 10 a.m. He pauses, then adds, but professional judgment includes acknowledging uncertainty. There are variables I couldn't measure. Actual air leakage through the collapsed shaft, CO2 absorption by coal and rock surfaces, metabolic variation among individuals. So I can say survival was unlikely without ventilation, but I can't say survival was impossible. Harrison writes this down, thanks Jimmy for his cooperation, and says that a formal investigation will be conducted in accordance with federal mine safety regulations. Jimmy nods, too tired to care about investigations or regulations or anything except getting home to the small apartment he shares with his mother in Farmington, 12 miles from the mine site. A company truck drives him there, arriving at 1:17 a.m. on March 9th. His mother, Grace Watkins, has been awake since receiving the notification at 7:30 a.m. yesterday that there had been an accident and her son was among those trapped. She opens the door before Jimmy can knock, takes one look at him covered in coal dust and holding his ribs, and pulls him into a hug that makes him gasp from the pain, but that he doesn't pull away from. Sleep doesn't come easily despite his exhaustion. Jimmy lies in his childhood bed, in the room where he grew up studying electrical theory from textbooks bought secondhand from departing technical college students, and his mind won't stop replaying the circuit. The moment when he touched the wires together and heard nothing for that terrible second. The sound of the motor starting, the feel of the wire getting warm under his hand. The calculations he did over and over. Voltage times amperage equals wattage. Wattage divided by motor efficiency equals actual power delivered. Actual power versus required power determines whether the system works or fails. Numbers that meant life or death. He finally sleeps at 3:30 a.m. and wakes at 11 a.m. to find his mother has let him rest while she fielded phone calls from reporters, mine officials, and people from town asking about his condition. The Charleston Gazette wants an interview. The United Mine Workers Union wants him to speak at a safety conference. The technical college where he took night classes wants him to give a guest lecture. Jimmy declines all of it. He's not interested in being famous. He's interested in going back to work, back to maintaining electrical systems, back to a routine where decisions don't carry the weight of 127 lives. But routine proves elusive. On March 11th, 3 days after the explosion, Jimmy receives a telegram from the West Virginia Mining Commission requesting his presence at a formal inquiry into the incident. The inquiry is scheduled for March 18th in Charleston, and attendance is mandatory. Jimmy takes a Greyhound bus to the state capitol, his ribs still wrapped in bandages, and finds himself sitting in a hearing room facing a panel of 5 mining engineers and safety officials. The questioning lasts 6 hours, covering every aspect of the improvised circuit: design, construction, monitoring, failure modes, risk assessment. Jimmy answers each question with the same factual precision. No embellishment, no dramatization, just technical details and calculations. The panel's final question comes from Dr. Richard Morrison, a professor of mining engineering at West Virginia University, and the inquiry's technical expert. "Mr. Watkins," Morrison says, "you modified a critical safety system without proper authorization, using materials not rated for the application, in violation of electrical codes that exist specifically to prevent accidents. These are serious breaches of protocol. However, the result was that 128 men survived an event that should have killed them. How do you reconcile these contradictory facts?" Jimmy thinks for a long moment before responding. "Dr. Morrison," he says finally, "protocols exist for good reason. They prevent improvisation that might seem like a good idea, but actually creates danger. In normal operations, I would never bypass safety systems or use unauthorized modifications. But this wasn't normal operations. This was a survival situation where the authorized systems had failed completely. The choice wasn't between protocol compliance and protocol violation. It was between trying something that might work and doing nothing while 127 men died. I chose to try. If that was wrong, if there was a better option I missed, then I apologize. But given the information available and the time constraints involved, I believe the choice was correct." Morrison nods slowly. "For the record," he says, "the panel's preliminary analysis indicates that your improvised system, while technically non-compliant with established codes, represented sound application of electrical principles under emergency conditions. We find no evidence of reckless behavior or negligent decision-making. The panel recommends commendation rather than censure." The hearing concludes at 5:30 p.m., and Jimmy takes the Greyhound bus back to Farmington, arriving at midnight. The formal commendation will come later, but what matters right now is that the experts have examined his work and found it acceptable. The circuit was sound. The decision was correct. The 127 men survived. The technical analysis arrives in Jimmy's mailbox on April 3, 1952. A 47-page report from the West Virginia Mining Commission titled "Investigation into Emergency Ventilation Procedures, Consolidation No. 9 Mine Incident, March 8, 1952. The report includes detailed engineering analysis of Jimmy's circuit, with diagrams reconstructed from his testimony and examination of the salvaged equipment. The analysis confirms his voltage calculations were accurate within 8%. The wire gauge he selected was appropriate for the current loads involved. The parallel connection of 128 lamp batteries was unorthodox but electrically valid. The report's conclusion states, "The improvised ventilation system created by electrician James Watkins represents an exceptional example of practical engineering under extreme conditions. While the methods employed violated established protocols, the underlying electrical theory was sound and the execution was competent." This incident demonstrates the importance of fundamental technical knowledge in emergency situations where standard procedures become inapplicable. But the report also includes a section titled "Systemic Failures That Necessitated Improvisation," and this section is harder to read. It documents the failures that made Jimmy's circuit necessary: inadequate maintenance of backup generators, insufficient emergency battery capacity, lack of redundant power systems, inadequate training for emergency procedures. The report identifies 23 specific safety violations or deficiencies that contributed to the crisis, and it makes 17 recommendations for improved safety standards across all consolidation coal operations. Jimmy reads this section 3 times, understanding that 128 men survived not because the system worked, but because the system failed, and one person happened to have the knowledge and tools to improvise a replacement. The Medal of Industrial Heroism ceremony takes place on April 15, 1952, in the West Virginia State Capitol Rotunda. Governor O.K. Pattison presents the award, a bronze medal suspended on a blue ribbon, to Jimmy in front of an audience of 300 people, including mine safety officials, union representatives, and 89 of the 127 miners who survived the March 8 incident. The governor's speech emphasizes courage and heroism and the finest traditions of West Virginia mining. Jimmy stands at attention in a borrowed suit that doesn't quite fit, his ribs still tender but healing, and thinks about the gap between how people describe what happened and what actually happened. Heroism sounds noble, intentional, like a choice made from strength. What Jimmy remembers is fear and desperation, and a frantic hour stripping wire while his hands shook and his mind raced through calculations trying to determine if theory would translate into practice quickly enough to matter. The speech ends. The medal is presented. Jimmy shakes the governor's hand, poses for photographs with officials who weren't there and don't understand what 14 hours underground feels like, and gives a brief acceptance speech that his mother helped him write. "I'm honored by this recognition," he says, reading from note cards because public speaking terrifies him more than electrical hazards ever have. "But I want to be clear that I didn't save 127 men alone. Foreman Thomas Riley made the decision to let me try an untested solution. Electricians Carl Henderson and Mike O'Brien helped construct the circuit. Every miner who stayed calm and conserved oxygen contributed to their own survival. What happened on March 8th wasn't one person being heroic. It was 128 people working together to survive impossible circumstances. The medal honors all of us." The audience applauds. The ceremony concludes. Jimmy returns to Farmington, hangs the medal on the wall of his bedroom next to his technical college diploma, and reports for work the next morning at 6 a.m. He's assigned to surface maintenance for 6 weeks while his ribs finish healing, then cleared to return to underground electrical work in early June. The mine itself reopens on May 2nd after extensive repairs and safety upgrades, including installation of redundant emergency power systems, with sufficient battery capacity to run ventilation fans for 24 hours. The upgrades cost Consolidation Coal approximately $380,000, spread across their entire West Virginia operation. But for the 127 miners who were underground on March 8th, the aftermath is more complicated than safety upgrades and official recognition. Carl Henderson returns to work but transfers to surface operations after 3 months, unable to shake the claustrophobia that developed during those 14 hours underground. Mike O'Brien continues mining for another 8 years before retiring early with lung problems. Thomas Riley works until his planned retirement in 1967, but later admits in an oral history interview that he had nightmares about the incident for years. Dreams where the battery dies and the fans stop and the air gets thick and heavy, and 127 men look at him asking why he approved the circuit, why he trusted a 19-year-old kid with their lives. Some miners recover faster. Daniel Wright, a 34-year-old father of 3 who was trapped in the tunnel, returns to work after 2 weeks and later tells a local newspaper, "After you've been that close to death and survived, the everyday dangers of mining don't scare you the same way. You realize that death is always possible, but so is survival, and worrying about what might happen doesn't change what does happen. You just do your job and trust your equipment and hope engineering beats probability one more day. It's a philosophy shared by many miners who learn to accept risk as part of the profession, but it's a philosophy that becomes harder to maintain after events like March 8th demonstrate exactly how thin the margin between life and death can be. The photograph that will become iconic is taken on March 12, 1952, 4 days after the incident. Photographer William Preston from the Charleston Gazette arrives at the mine with his equipment and asks to recreate the scene for documentation purposes. Mine officials agree, seeing the value in preserving the moment for training and historical purposes. They set up in a side tunnel that wasn't damaged in the explosion, bringing in the actual car battery Jimmy used, a selection of the lamp batteries from the array, and representative samples of the salvaged wire. Jimmy, wearing clean coveralls and his safety helmet with lamp, kneels beside the battery setup and rests one hand on the connections, while Preston adjusts his lights and camera angles. The exposure takes 30 seconds, requiring Jimmy to hold perfectly still while the camera's shutter remains open. In that 30 seconds, he thinks about the gap between this staged recreation and the actual event. The actual event happened in darkness, except for headlamps, with the constant sound of 127 men breathing, with the smell of methane and sweat and fear, with the weight of broken ribs making every movement painful, with the knowledge that every second the circuit didn't work was another second closer to catastrophic failure. This recreation has professional lighting, no ambient danger, no time pressure, no actual stakes. It captures the physical arrangement, but misses the essential truth, that improvisation under extreme pressure feels nothing like posing for a photograph 4 days later when everyone is safe. But Preston is a professional photographer with 15 years of experience, and he understands that photographs document moments, not feelings. The image he creates is technically excellent. Sharp focus on Jimmy's face and the battery setup, good contrast showing the tangle of wires, depth of field that keeps both the foreground equipment and the tunnel background in acceptable focus. The photograph will be published in the Charleston Gazette on March 14th, reproduced in newspapers across the country within a week, and eventually included in mine safety textbooks where it will illustrate emergency procedures for decades. Students in mining engineering programs will examine that image and discuss the technical aspects of Jimmy's circuit without understanding the fear or exhaustion or desperate hope that accompanied its construction. Academic interest in the incident extends beyond engineering programs. Dr. Patricia Chen, a psychology professor at Marshall University, publishes a paper in the Journal of Applied Psychology in September 1952 titled Decision-Making Under Extreme Stress, a Case Study from the Mining Industry. The paper analyzes Jimmy's decision-making process during the crisis, identifying factors that contributed to successful outcomes: technical knowledge that provided a framework for improvisation, previous experience with similar systems that built pattern recognition, personality traits including low panic response and high tolerance for uncertainty, and crucially, support from authority figures, Riley, and collaborators, Henderson O'Brien, that validated his approach and provided practical assistance. Chen's analysis includes interviews with Jimmy conducted in June 1952, during which he describes his thought process in detail. The interviews reveal something interesting. Jimmy didn't experience the circuit building as a single continuous effort, but as a series of discrete problems, each solvable with available resources. Problem: fans need power. Solution: use available batteries. Problem: batteries provide insufficient voltage. Solution: accept reduced fan speed. Problem: batteries have limited capacity. Solution: add more batteries in parallel. Each solution created new constraints, but none of the constraints were absolute barriers. The psychological insight, according to Chen's paper, is that by breaking an overwhelming situation into manageable pieces, Jimmy maintained cognitive function and avoided the paralysis that extreme stress can induce. The interview transcripts also reveal Jimmy's doubts, the moments when he questioned whether his improvised solutions would work. After connecting the initial car battery circuit, he estimated a 60% chance of success. After adding the lamp battery array, he revised that to 75%. Even at the end, with rescue teams breaking through and all 128 men still conscious, he maintained a small percentage of uncertainty because unexpected failures are always possible. This calibrated confidence, neither overconfident nor paralyzingly doubtful, represents optimal decision-making under uncertainty, according to Chen's analysis. The United Mine Workers Union invites Jimmy to speak at their annual safety conference in Pittsburgh in October 1952. He reluctantly agrees, spending a week preparing a presentation that focuses on technical aspects rather than personal narrative. The presentation, titled Emergency Electrical Systems, Theory and Practice, includes detailed schematics of the circuit, voltage calculations, and a discussion of minimum operational thresholds for various types of equipment. The audience of 400 mine electricians and safety officials listens attentively, asking technical questions about wire gauge selection, parallel versus series connection strategies, and methods for estimating remaining battery capacity without proper testing equipment. But during the question period, a young electrician from a Pennsylvania mine raises his hand and asks the question that's actually on everyone's mind. How did you stay calm enough to think clearly when you knew 127 men would die if you made a mistake? Jimmy considers this for a long moment before answering. I didn't stay calm, he admits. I was terrified. My hands shook. My mind raced. I had trouble breathing, partly from broken ribs, but mostly from fear. But being calm isn't a requirement for doing necessary work. You can be scared and still remember your training. You can doubt yourself and still try solutions. Courage isn't the absence of fear. It's the decision that something else matters more than fear. The room is silent for several seconds after this answer. Then someone starts clapping, and the applause spreads until all 400 people are standing, and Jimmy understands that what they're applauding isn't the technical brilliance of his improvised circuit, but the more fundamental truth that sometimes survival requires accepting fear and working anyway. The applause continues for 2 full minutes, and Jimmy stands at the podium feeling awkward and honored and deeply uncomfortable with being treated as special when he was just an electrician doing electrical work under difficult circumstances. Jimmy returns to his normal work routine after the conference, maintaining electrical systems in consolidation mines across West Virginia. He's promoted to senior electrician in 1954, supervisor in 1957, chief electrical engineer for the entire operation in 1962. The career progression is faster than typical, aided by his growing reputation as the electrician who saved 127 lives, but also by competent work and accumulating experience. By 1965, he's responsible for electrical systems in 14 mines employing 3,200 workers, and he's trained 47 electricians in both routine maintenance and emergency procedures. The training he provides includes a section specifically on improvisation, how to assess available resources, how to calculate minimum operational thresholds, how to make risk decisions when proper procedures become impossible. He teaches students to carry mental inventories of electrical principles that remain valid regardless of circumstances: Ohm's law, series versus parallel circuits, power calculations, heat dissipation requirements. Procedures change, he tells classes of new electricians. Regulations evolve, equipment gets updated, but physics doesn't change. If you understand the fundamental principles, you can adapt to any situation. You can figure out what will work and what won't, even when nobody's written a procedure manual for your specific problem. The lesson is practical, drawn from experience rather than theory. Several of his students will later credit this training with helping them solve emergency problems in their own careers. A 1967 incident where an electrician jury-rigged a temporary lighting system after a power failure. A 1971 case where another electrician bypassed a damaged pump controller to prevent flooding. A 1974 situation where yet another used car batteries to power communication equipment. None of these incidents make national news. None result in medals or recognition. But they represent the same fundamental skill, the ability to translate electrical theory into practical solutions when standard procedures fail. The Consolidation No. 9 mine operates until 1968, when another methane explosion kills 78 miners, despite all the safety improvements implemented after 1952. That disaster, occurring at 5:30 a.m. on November 20th, 1968, results from a different failure mode, a spark from a damaged conveyor belt igniting accumulated methane in a sealed section. The improved ventilation systems work exactly as designed, but they can't prevent an explosion in an area where gas has accumulated behind a barrier. The tragedy leads to the Federal Coal Mine Health and Safety Act of 1969, which Jimmy helps draft in his capacity as a recognized expert on mine electrical systems. The 1969 Act includes provisions directly derived from lessons learned in 1952, requirements for redundant emergency power, specifications for battery capacity sufficient to sustain ventilation for minimum 24 hours, mandated training for all mine electricians on improvisation techniques, and establishment of minimum air quality standards with continuous monitoring. Jimmy testifies before Congress during hearings on the Act, providing technical expertise and emphasizing the importance of both proper safety systems and the training to improvise when those systems fail. His testimony, delivered in the same matter-of-fact tone he's used to describe technical problems for 17 years, helps convince legislators that effective mine safety requires both engineering solutions and human competence. The Act passes in December 1969 and takes effect in March 1970. Its implementation costs the mining industry approximately $260 million across the United States, but mining fatality rates drop by 38% within 5 years. Jimmy retires from Consolidation Coal in 1975 at age 42, leaving mining to work as an electrical contractor in Farmington. The early retirement surprises some people, but Jimmy explains it simply. "I've spent 23 years underground. I've trained good people who can do the work. I want to see more daylight." He'll continue consulting on mine safety issues until 1990, but his primary focus shifts to residential and commercial electrical work, problems with lower stakes and fewer opportunities for catastrophic failure. The 127 miners who survived March 8, 1952, scatter across the following decades. 73 continue working in mining. 54 leave the industry for safer professions. By 1990, 42 have died from various causes: lung disease, heart failure, accidents, cancer. By 2000, only 28 remain alive. Thomas Riley, the foreman who authorized Jimmy's improvised circuit, dies in 1989 at age 81 from complications of black lung disease. His obituary mentions his 38-year mining career and his role in the 1952 incident, noting that he often said the hardest decision of his career was trusting a 19-year-old electrician with 127 lives because the alternative was watching those lives end. Carl Henderson, one of the electricians who helped construct the circuit, dies in 1993 at age 74. His family, sorting through his possessions, finds a notebook containing detailed diagrams of the lamp battery array he helped assemble, with annotations about wire routing and connection methods. The notebook has clearly been referenced many times over the years, its pages worn and stained but carefully preserved. A note on the inside cover reads, "March 8, 1952. The day I learned that engineering isn't about following procedures. It's about solving problems with whatever tools are available. Never forget this." Mike O'Brien, the other electrician who assisted with the improvisation, survives until 2003, dying at age 84. In a 1998 interview for an oral history project documenting West Virginia mining, he reflects on the incident. "People ask if we were scared, and of course we were. But fear is just information. It tells you the situation is dangerous, but it doesn't tell you what to do about it. What we did about it was trust Jimmy's calculations and build the circuit he designed. Was it certain to work? No. But certain failure is worse than uncertain success. So we tried. That's not heroism. That's just basic problem solving applied to a serious problem." Jimmy Watkins lives until 1998, dying at age 65 from lung cancer that probably originated during his 23 years breathing coal dust, despite all safety equipment. His obituary in the Charleston Gazette runs 800 words, covering his career, his family, his community involvement, and inevitably, the March 8, 1952 incident. But what the obituary cannot capture, what no collection of facts can convey, is the weight Jimmy carried for 46 years after that morning. The knowledge that 127 men lived because his improvised circuit worked, and the parallel knowledge that if his calculations had been wrong, if the wire had been too thin, if the connections had failed, those same 127 men would have died while he watched. Success and failure balanced on such a thin edge, decided by whether 12 volts could make a motor turn despite needing 240. The car battery, serial number E42876, remains in its climate-controlled case at the West Virginia Mining Museum. School groups visit regularly, teachers explaining how basic electrical principles saved lives, students taking notes for reports. But the battery itself says nothing. It's just a 12-volt automotive battery, manufactured by Exide in 1948, originally installed in a 1949 Ford pickup truck, later repurposed for mine emergency equipment. It has positive and negative terminals, lead plates and sulfuric acid electrolyte, a plastic case designed to withstand vibration. Everything about it is ordinary except the moment when Jimmy Watkins connected it to a circuit that shouldn't have worked but did, that violated regulations but saved lives, that proved theory translates into practice if you understand principles deeply enough to improvise when procedures fail. The final word on the incident comes from Dr. Alexander Morrison, who served on the 1952 investigatory panel and later became Dean of Engineering at West Virginia University. In a 1985 lecture to mining engineering students, Morrison reflects, "The March 8, 1952, Consolidation Number 9 incident represents a paradox for engineering education. We teach procedures and regulations and proper methods because following established protocols prevents most accidents. But we also need to teach the underlying principles that allow competent improvisation when protocols become impossible." Jimmy Watkins saved 127 lives not because he knew the procedure for emergency ventilation. That procedure required resources he didn't have, but because he understood electrical principles well enough to create a new procedure using available resources. That's the highest level of engineering competence, the ability to apply theory to novel problems without guidance or precedent. Morrison continues, "Every electrical engineer should study this case and ask themselves, could I have done what Watkins did? Could I have assessed available resources, calculated operational thresholds, estimated success probability, and then implemented a solution knowing that failure meant death for 127 people? The honest answer for most of us is probably no. Not because we lack the technical knowledge. Any graduate of this program knows Ohm's law and motor theory. But because we lack the courage to trust our knowledge enough to bet lives on it. Watkins had both knowledge and courage. That combination is rare and precious and worth infinitely more than perfect compliance with regulations written for different circumstances. On March 8, 2002, exactly 50 years after the incident, the 19 surviving miners from that day gather at the Consolidation Number 9 mine site for a memorial ceremony. The mine has been closed since 1968, its entrance sealed, but the location is preserved as a state historical site. A bronze plaque commemorates the incident, listing all 128 names and the simple text, "On March 8, 1952, these men survived a mine collapse through cooperation, courage, and the ingenuity of a 19-year-old electrician who powered ventilation fans with a car battery and proved that engineering principles can overcome impossible circumstances." The 19 survivors, now ranging in age from 67 to 84, gather before the plaque for a photograph that mirrors the group photos taken in 1952 immediately after rescue. But the mirror is imperfect. 108 men are absent, claimed by time and disease and the ordinary mortality that waits for everyone. The survivors who remain look at the plaque, at the sealed mine entrance, at each other, and share a memory that will die with them. The sound of fans starting up in darkness, the feel of air moving after minutes of stillness, the overwhelming relief of understanding that someone had figured out how to keep them breathing for a few more hours. It was enough. It was always going to be exactly enough. Because Jimmy Watkins did his calculations correctly, and physics doesn't care whether a circuit is authorized or improvised, only whether it's complete and functional. The last of the 128 survivors, Martin DeMarco, will die in 2018 at age 98. His obituary mentions his long life, his family, his career after leaving mining in 1954. And it mentions briefly that he was one of the miners trapped in the Consolidation Number 9 collapse of 1952, one of the 128 who survived because a teenage electrician refused to accept that proper procedure mattered more than survival. With DeMarco's death, the direct memory of that March morning disappears. What remains is documentation, photographs, investigation reports, technical analyses, oral histories, and most importantly, the principles that Jimmy Watkins demonstrated. Those principles transcend the specific incident. They apply everywhere human survival depends on technical competence: aerospace engineering, maritime safety, emergency medicine, disaster response. The principle that understanding theory enables improvisation. The principle that sometimes violating procedures is necessary to serve the deeper purpose those procedures were meant to accomplish. The principle that courage isn't fearlessness, but rather the decision that solving the problem matters more than avoiding risk. And perhaps most importantly, the principle that ordinary people with ordinary tools can achieve extraordinary results when circumstances demand it, and training provides the framework for action. On the wall of the West Virginia Mining Museum, beside the preserved car battery, hangs a final photograph taken in 1975 on Jimmy Watkins' final day working for Consolidation Coal. The image shows Jimmy, age 42, standing outside the entrance to a mine in clean coveralls, holding a toolbox in one hand and a hard hat in the other. He's looking directly at the camera with an expression that combines satisfaction, relief, and perhaps a trace of the knowledge that will stay with him until his death 23 years later, that for 14 hours on a March morning in 1952, he was the circuit between 127 men and death, and the circuit held.